So our next speaker is Gilles from IDEA Software in Madrid. Gilles got his PhD in 1980 from the University of Manchester and has worked on a number of different areas since then. He has worked on programming languages, program verification, security, crypto, formal foundations of mathematics. And so since he joined IDEA, he mostly worked on crypto and differential privacy, and that's also going to be the topic of his talk today.
Okay, so now we go. So what I will be presenting today is actually work which we started many years ago while I was still in INRIA Sophia Antipolis in France, and it's work with primarily my former colleagues there, and it's actually about trying to apply programming languages to cryptography initially and then to privacy. So I have to stress that I've been trying to work in the area of cryptography for the last 10 years, and I still don't feel like a cryptographer. These guys have a very great intuition that I am lacking. But on the other hand, what I think we managed to achieve is to show that applying programming language techniques to these fields of cryptography and privacy can actually be very fruitful and kind of bring a complementary view to what these guys are doing. So the work which I will be presenting today is kind of a more foundational nature. We've been doing some additional work on more practical aspects like verifying crypto implementation, especially against side channel attacks and so on. I will not be talking about this, but my colleagues have web pages on where all the papers are listed, and you can go and check it there. And probably if you go to DBLP, you can also grab some of our paper. So what I will be presenting today is kind of essentially the goal is to try to apply formal verification, to try to carry the kind of proofs that cryptographers are doing. And so a primary kind of difficulty when you try to do this is that most of program verification actually reasons about a single execution of the program. For example, you want to know that when you feed a particular input to a program, you will get a result, which is, for example, the square root of the input. So that's a standard functional verification. Security properties are, in fact, a bit different. They look at a kind of property which are called relational. And essentially, relational property are properties that reason about two executions of a program or the relationship between two programs. So I call it relational properties. There are some other people who call it differential properties. And so essentially here what we have is you have, let's say, a single program. You have the natural generation to two program, but you have a single program and you have the two inputs which are related by a condition. You want that the output are related by condition, okay? And so there are multiple instances of this. Very simple instance is monotonicity. So a program is kind of doing monotonic computation. Let's say it's doing some computation over integers, taking integers as input and returning integer as output. And then you say, okay, if I feed two integers and the first one is smaller than the other, the second one, then the first output will be smaller than the second output. So that's a kind of a very simple property, and it's kind of a very basic example of a relational property. A slightly more interesting property that plays an important role, for example, in the verification of cyber-physical systems. So when you have kind of programs that are interacting with environment and so on, and you would actually like that if you have very small changes in the parameters that you are feeding to your program, you would get very small changes in the output, because you don't really want that a very small variation in the parameter will create huge change in the behavior of the program. So the idea of stability at a very high level is like if your inputs are similar, then the outputs will be similar. And there can be many different notions of stability. There are actually many notions of stability within the context of CPS, but in a broader setting, you can think about similarity in many different ways. So one possible instantiation of stability is a kind of non-interference, which is in fact a security property. And a non-interference is actually saying that your kind of world is split in two. You have some public values, you have some secret values, and what you would like is like when you run a program and you can actually observe the public output of the program. It doesn't leak any information on the secret input. Okay, so the notion of similarity here is like the two memories are equal in their low parts. And so a lot of work on a kind of a relational property, at least from my perspective, was started from the point of view of non-interference, and there have been many generalization of this work. So here I'm looking about relational property, but there is a general framework that was developed by Clarkson and Schneider, which is called hyper property, which is a much more general setting. I will not go into this in this talk, but if you're interested, they have a very nice and well-written paper. I mean, these people, they speak proper English and they write very nicely. It's kind of a pleasure to read what they write, so I mostly recommend their paper. And so for what actually is going to concern us in this talk, we are interested in relational property, but on top of this, we are not interested in relational property for deterministic program. We will be interested in relational property for a probabilistic program. Okay, so if you actually look at cryptography, there is a huge trend, or kind of it's the majority trend since the invention of provable security by Goldwasser and Micheli to try to look at security notions which are probabilistic and to develop cryptographic algorithm which actually uses probability. So if you want to reason about this, you should be able to reason about probability. So let's try to see what this relational property means in the probabilistic setting. So the first kind of generalization is that of monotonicity. So there is a counterpart to monotonicity in the probabilistic setting, which is called stochastic domination. So now you have to think that your program is going to take an input and returns a distribution of values. And so the counterpart of monotonicity is actually that if you start with two outputs, 1 and 2, and such that the first input is smaller than the second one, then for every possible value k, the probability that the first output is going to be greater than k is going to be smaller than the probability that the second output is going to be greater than k. Okay, so that's the probabilistic counterpart of monotonicity. For stability, things are slightly easier. What you want is like you have related input and you want your two probabilities. So for any arbitrary value k, you want that the probability that the first output is going to be equal to k is similar to the probability that the second output is going to be equal to k. Okay, so here if you think about similar, like a notion of being close, you will see that you have actually two notions of distance. So you have the notion of distance on your input space, so if they are integers, and then you have a notion of distance on the probability space, and there are many actually possible notions for two distributions being equal. One, for example, is a statistical distance. And then you have a generalization of non-interference, which is probabilistic non-interference, and again, you can think about it as some kind of instance of stability. So you just instantiate the notion of being close, and so in the first case, you will say you are equal on low input, and then you require, for example, that probabilities are equal. Okay, there are weaker notions where you require that the probability are close. So what we're going to be after is try to find general methods to verify this kind of property. And the way we're going to do it is actually looking at something that comes from probability theory. And so this is actually something which we discovered after the fact. So we had been working on this topic for many, many years, coming up with a notion that looked okay to us. but we were very ignorant, so we didn't know that it was well studied in probability theory, and we recently found this out, which is a kind of a relief to us, because you never know whether you come up with some half-baked mathematics, and so when you actually read that this is something that proper mathematicians have studied, it was a very big relief. And so why do mathematicians study probabilistic couplings? Well, primarily probabilistic couplings, which I will explain in a minute, they are actually used to analyze convergence of Markov chains. And so the basic idea of a coupling, and so by the way, okay, so just a bit of excitement. I mean, there are really, really many applications of this probabilistic coupling and convergence of Markov chain to security, to models of molecular evolution, to kind of many, many different settings. So this is really, really cool as far as applications are concerned. And so the main idea of probabilistic coupling is like you have two probabilistic processes, and you want to relate them in some way. Okay, and you can think as each probabilistic process as doing some kind of, doing some random sampling, nano-deterministic computation, and the other one is going to do the same, random sampling and the deterministic computation. And the basic idea of coupling is rather than try to reason about the two processes in isolation, you're going to build a single process which is going to emulate the behavior of the two. And the way you are going to do this is actually take the random sampling and do a single random sampling, which is kind of going to be shared between the two. So in a way, rather than trying to have the two things behave independently, you are just going to try to force them to be together in a certain way. And so you kind of coordinate the random sampling in such a way that you will establish some kind of property that can be used as some kind of invariant in your reasoning. Okay, so that's essentially this. You have, instead of having two independent processes, you're just going to have a single process in a bigger space, and the single process is just going to emulate the behavior of the two. And so this is a way you can achieve invariant, but also you can later on also use the single process to analyze its probabilistic properties. So there are some more elaborate notion of coupling, like path coupling or shift coupling, that actually take advantage of this. Okay, so why is this very good to look at this kind of probabilistic coupling? Well, there are actually two things. So as I mentioned, by and large, most of the work in program verification is about verifying trace property of deterministic program. And what we have to do here is actually verify relational property of probabilistic program. And so what's the best way to do this if you're very lazy, which is our case, is like you try to map back the new problem you have to something which people already know how to solve. And this is essentially what probabilistic coupling allows you to do, because you're going to reason about relational property of probabilistic program, but you will never have to think about probability. That's kind of the magic of coupling. And on top of this, the way things are set up is primarily going to look very much like standard verification. And in fact, I mean, you can even go further and give a direct reduction, but this is not what we do. And the other thing is really that it's compositional. So, you know, compositionality, when you try to do program verification, it's like a big deal, and everything you try to do has to be compositional and so on. But when you go and see the way other people do their proof, either in crypto or in differential privacy, I mean, they don't really care about compositionality. They do their proofs as proper mathematicians. But sometimes it really strikes back, and they have a problem. And then, I mean, using our methods, we can actually have a much better way of scaling or adapting proof. I will give one example of this at the end of the talk, where actually trying to do things in this kind of straitjacket where we do proofs in a compositional way and so on, actually gives us a lot of leverage on trying to adapt results from the literature, whereas the domain experts, they have a bit of a hard time to try to go through their non-compositional proof and fix it. Okay, so how are probabilistic coupling defined? Well, assume you have two distribution over a set A. So in fact, you could actually assume that x1 is a distribution over A1 and x2 is a distribution over A2, but for the purpose of this talk, I just assume they're over the same set. And also maybe I should mention that everything in this talk and everything in the work that we did is about discrete distribution. You can actually consider generalizing this to continuous distribution. You just have all these measurability issues that show up all the time, and we are too lazy to deal with this, but in principle it should extend. And also, I mean, like a good excuse that is everything in crypto is finite, so you don't really have to go to the continuous case. In differential privacy, it's not so, because people took a look about distribution over the reals, but we started with crypto and we started with discrete, and we kept on with this. So the idea of building a coupling is this. You are just given two distribution, x1 and x2 over some finite set, of a discrete distribution. The set doesn't need to be discrete, but let's assume it's discrete for the purpose of this talk. So you have your two discrete distribution, and what you would like to do is build a single distribution which is going to emulate the behavior of the two. And so what is this? This is actually a distribution of pairs, okay? In such a way that when you take the first marginal, you get the first distribution, and when you take the second marginal, you get the second distribution. Okay, so there is this notion of projection, which is actually corresponding to the notion of marginal. So that's the formal definition. This is the first projection. This is the second projection. And the idea of the projection is like, for example, when you take the first projection, you're just going to, and you apply it to A1, you're going to sum over all A2, y of A1, A2, okay, where y is your distribution. Yeah, I mean, there are two arbitrary distributions. You don't know. You don't know. I mean, in general, there are just two distributions. Okay. So that's the idea of coupling. And it looks like a very simple tool. And in fact, it's actually a very, very powerful tool. So let's see how it works. How can we couple, let's say, two coin toss, okay? So you're just flipping a coin, probability half to be head, probability half to be tail, and you do the same on the second process, and you want to build a couple for them. So actually, there are many ways to do so, and each way you're going to do it is going to give you some kind of property that you are going to use further on for your reasoning. So it's kind of giving you some kind of invariant that you will be able to use in the end. So one way to actually do the coupling is like you require that x1 is going to be equal to x2. Okay, so there is okay, so maybe. So here you just flip a coin, you get half, half, and this is 0, 1, this is 0, 1, half, half. So one way is just, you're just going to weight half to this and weight half to this, okay? So this is actually the distribution that gives probability half to 0, 0, and probability half to 1, 1. And this actually forces the relation x1 is equal to x2, okay? So that's the first way you can do this. The second way you can do this is actually, again, you have your distribution. Here, what you want to enforce is actually x1 is different from x2. So what you're going to do is you're going to give weight half to this and weight half to this. Okay, so this is actually you give probability half to 0, 1 and probability half 1, 0. And you see that you get x1 is different from x2. Okay. There is another way where you just give a weight a quarter to each element. Then the property you enforce is just true, which is not very interesting. So there are actually many choices, and the choices depend on which application you have in mind. And essentially, there is no kind of general, I mean, there are some general ways of building couplings. There is a notion which is called optimal coupling, and which is kind of used for a particular theorem, which I will show later, which is called Strassen's theorem. But in general, building coupling is kind of an art. It's like coming up with invariants or whatever. You have to kind of tweak things in a way which is going to be suitable for you to be able to do your verification. Okay, so there is a kind of a bit of craft here that needs to be used. But once you have this, you have kind of a generic way to try to do your verification. And so in particular, in our verification, what we try to do, we look at the notion, which is an elaboration of coupling, which I have already alluded to in the kind of previous slide. We want to build couplings which actually satisfy a property. And so this is a notion which is called lifting. So it's like coupling, except that this type, on top of the two distributions, mu1 and mu2, you actually have a relation R, a binary relation over A, and you want that the kind of coupling distribution that you will be building actually has its support included in this relation. By which I mean that every element which has a non-zero probability with respect to this distribution should be in the relation. And so that's the notion of lifting here. So you say that mu1 and mu2 are related by the lifting of R if and only if there exists a distribution mu such that mu is a coupling for mu1 and mu2, and the support of mu is actually included in R. Okay, and so this notion of lifting is actually used very much also in probabilistic process algebra, and this is actually, in my opinion, the kind of right formalization of the notion of coupling, because essentially when you read these mathematical papers, they give you the definition of coupling, and always the fact that it satisfies the relation is kind of implicit in the kind of reasoning they do, but they're always building their coupling in such a way that it satisfies a relation. And so that's kind of the central notion in what we are doing. If you are kind of familiar with reasoning and you think about this as something that will actually help us or that will actually be used to explain the meaning of post-condition, you see that we're heading towards a logic where kind of the notion of valid judgment has some kind of existential quantification hidden in, which means that it will be kind of a weird logic. But this is actually something which is very useful in practice. So let's look very quickly at one example, which is how you can use coupling to actually prove convergence of random walk. So you have a random walk where you start at a position, an arbitrary position, and then what you want to do is like you flip a coin, move left, move right. I don't have any stopping kind of condition. I keep on forever. What I want to show is like in the end, after I've been doing sufficiently many steps, the initial position doesn't matter so much. Okay, so what are we going to do? We're going to build a coupling in the following way. Assume that the two walks, so we have walks that start at position P1, walks that start at position P2, and they keep on going. And so what we have to do is at each step, we have to decide how we're going to coordinate the random flip that we are doing. And so what we are going to do is very simple. If the two walks are already together, they will actually take the same coin flip. So if it's head for one, it will be head for the other. Okay, and then because they are already together, the coin flip is the same, they will move in the same direction. Okay, so if we start together, we keep on together. Now assume that the two walks have not yet met. So what you will actually do is like you will make them go in mirror direction. Okay, so if this one moves away, this one will move away. If this one gets closer, the other one will get closer. Okay, and so why is this interesting? This is interesting because as soon as the two walks are going to meet, they're going to stay together. And because we have arranged them in the way that they kind of mirror each other, if they are not together, you can actually prove a result that with probability 1 they will end up meeting. Okay, so they will end up meeting, and once they meet, they stay together. So you have this convergence result. And how this is going to be formalized mathematically? So you have this notion of Strassen theorem, which is essentially saying, oh, if you want to measure the statistical distance or total variation distance between the two distributions, you can actually, which is going to be used as the measure of convergence, you can actually upper bound it by the probability that y1 is different from y2, where y1, y2, this pair is sampled from the distribution y, where y is actually a coupling of x1 and x2. Okay, so I gave you the coupling, and you have this result, and you have to show that this probability with the coupling I gave you is very small. And this is actually easy to establish from the fact that when you have a random walk with a kind of termination condition, you will terminate with probability 1. Okay? So using coupling, we have this relational Hoare logic for probabilistic program. And so this is something that looks very much like Hoare logic, but we now have 2 programs instead of 1, and essentially the precondition and the postcondition, instead of being predicates on states, they are kind of relation over states, and essentially, so here actually for simplicity, what I'm assuming is like C1 and C2 are operating over different program variables, so I can actually consider the divergent union of 2 memories, and essentially what I'm saying here is like this judgment is valid if I start from memories that satisfy the precondition, then I can actually build a lifting for the distributions which are obtained by executing C1 on M1 and C2 on M2. Okay, and this lifting has to be related to Q. And so this looks like kind of very esoteric, but for most of the application that we have in mind, we are actually using this fundamental lemma, which is essentially saying that if my postcondition is of a particular shape, okay, which is saying like some event on the first memory implies some event in the second memory, then I have this inequality between the probability of the 2 events. Okay, and this is actually fairly limited as far as you can think, because you have 2 probabilistic processes, and the only thing which you can actually do is kind of establish some inequality between them. So you could think, oh, I might be interested in something which is more general, where this is an arbitrary function of this probability, and this is an arbitrary function of this probability. It turns out that for most applications, or for all applications in cryptography, this is actually sufficient. Okay, so we have a logic which allows us to emulate kind of all the reasonings in cryptography, and so we have kind of program logic for this, and so the rules are very much like Hoare logic. So you have this sequential composition rule, which is as expected. So if you want to analyze sequential composition, you just have to find some intermediate assertions and establish the first part and the second part. There is something interesting with the kind of more complex rule which have some control flow. So here, I mean, this is actually a fragment of the system. They are kind of more general rule, but the kind of more obvious rule for a relational logic is like where the program on the left and the program on the right have actually the same structure. So here they are both if-then-else statements. And also you are working under the assumptions that the 2 guards are equivalent, which means that the 2 programs have the same control flow. Okay, now if the 2 guards are equivalent, then what you have to do is like if you want to relate these 2 if-then-else, you just have to look at the true branch and relate them, which is what is done on the left premise, and look at the false branch and relate them, which is what is done on the right premise. Okay, and then you have a rule for loops, and you see again that for loops you require the same control flow, and then you just have to show that when the kind of loop, so you have to prove the loop invariant under the assumption that the 2 conditions hold. But then what you have to prove in order to ensure that they have the same control flow in post-condition, you also have to prove that the guards are equivalent. So they either become both false or they stay both true. So recently we had a generalization. So the problem with this two-sided rule, which I showed you, is that the logic is not relatively complete, because if you are actually have two programs that don't have the same control flow, you cannot say anything about them. And we recently came up with rules that actually help making the logic relatively complete. It's a bit complicated, so I won't go into the detail. It's actually a simplification of the real rule. We probably junked half of the premise, so you can see that the real rule is more than ugly. But essentially here what we're trying to say is like you have to come up with an invariant which is maintained when you execute the two loop body in lockstep, or each loop body individually. Okay, so that's the kind of gist of the proof. It's slightly more complicated than this, because you have to make sure that, none of the two loops stop, so that's why we have this kind of conditions on termination, and we have some additional condition, but the gist of the idea is like your invariant has to be preserved both when you execute the two loop body in isolation, or in lockstep, or each of them in isolation. And that's actually something very useful. I don't know why it took us almost 10 years to get there, but this is something which we needed. Okay, and very quickly about the rule for random assignment. There is an obvious rule for random assignment, which is derived from the definition of semantic validity. In practice, what we end up doing is something which is slightly weaker. So what is implemented in our tool is a weaker rule, which is showed here. And this weaker rule is interesting because it actually shows there is a relationship between kind of reason or building probabilistic coupling and counting. So if you're assuming, for example, that these two probability here, so here what you have to do, so there's a typo here, it should be a mu1 and a mu2, but essentially in order to, this also explains a bit the magic, because we're reasoning about this probabilistic program without ever mentioning probabilities, and this is because to some extent when you do probability over discrete sets or discrete distribution, what you end up doing is some kind of counting, and showing equivalence of distribution is about the same as proving the existence of a bijection that satisfies certain property. So that's what we are doing here, okay? And so this is probably kind of a bit mysterious, but I think that what I want to say is like there is a rational explanation why we can reason about probabilistic program without ever mentioning probability. Okay, so let me move very quickly to applications. So first, some application to cryptography. I won't go too much into the detail because I didn't know how much you know about crypto, and this is actually also sometimes a bit long to introduce, but so we have a tool called EasyCrypt, which is an interactive proof assistant, which has a proof engine which looks very much like SSReflect, which is some kind of add-on to Coq. But we have a back end to SMT solvers and computer algebra system. And using this system, we've been verifying many examples from the crypto literature and kind of from all kind of application domains. So, you know, like if you're a cryptographer, you go to a crypto conference, and at some point you see half the guys go out because they say, yeah, this is symmetric crypto, so they go out. And then the next time you see kind of the other half of the guys going out, and they say, this is asymmetric crypto, so they go out. And what is very nice with formal verification is like our methods are completely kind of applicable to all kind of different settings. So we apply them to basic construction, key exchange protocol, zero knowledge protocol. We're now applying it to stuff like gobbled circuits, verifiable computation. We have a small project with NIST, which is the National Institute of Standard and Technology, where we're formally verifying their new standards for hash function. In spite of the austerity, there is still a company in Spain which is kind of doing interesting stuff on e-voting, and we are working with them on formally verifying their protocols. So we've been doing quite a few examples. And why is this interesting? Well, this is actually why we started working on this. Like around 2004, there were a couple of papers by prominent cryptographers that actually claim that they have a problem with their crypto proofs because they have very long proofs, and sometimes their proof is a mess. So it's very often the case that you will have a kind of construction or protocol that has been standardized and that has a proof, and people keep on finding flaws in the proof for many, many years. So, I mean, there are different levels where the proof can go wrong, or where the security can go wrong. It can be at implementation level, so there can be many, many attacks there. But it can also be that in the mathematical analysis that they did of the security of their cryptographic construction, they just did something wrong. And this is what these guys were worried about, and this is the kind of problem that EasyCrypt tackles. I have to say that, I think we reached the point where actually with our tools we can formalize arbitrary crypto provided you have a kind of infinite resilience to a machine check proof. So it's just a question of how much suffering you're willing to go through in order to complete proofs. Okay? Later on, we got excited about this kind of different thing, which is called differential privacy. And so differential privacy, which I will introduce in a moment, but is based on in order to adapt our result to differential privacy, we have a generalization of our logic where we also carry some quantitative values, and these quantitative values are related to a privacy budget. And essentially, for this, we have a notion of approximate lifting, and this notion of approximate lifting makes a distance between distribution intervene. And so what you are changing here is like instead of having a single witness, you have two witnesses, and it's two witnesses related by some notion of distance. Peter, I don't know when I'm supposed to stop. Okay, so I will go very quickly. Okay, so I will just tell you differential privacy and I will skip all the rest. So the basic idea of differential privacy is like you have a kind of a database and people are making queries to database, and this database is containing private information. And what you want is actually you want that people are willing to give their private information in the database because they know that no information about them will be leaked. Okay, and so there have been many attempts to try to come up with ways to ensure that this stuff is possible, but differential privacy is actually different in the sense that it's coming from the crypto community, and what they try to do is give a precise mathematical definition of what you want to achieve, so that people can convince themselves that if computation is differentially private, then it kind of protects your privacy. And then once you have this definition, you try to build a kind of algorithm that satisfies this. So the basic idea is like you have two scenarios, and that's why it's relational. In one scenario, one person puts his data in the database, and the other scenario, it doesn't put his data in the database. Then you run the query on the two databases, and what you want to get is kind of two distributions that are very close together. So the red line doesn't show on my slide, but there should be a red line. And so you want them to be very close. And essentially, this is going to be modeled by saying, oh, a randomized algorithm is differentially private if for two databases that are adjacent, so that means that they only differ in one entry. There is this inequality that holds, and this inequality actually captures a notion of distance, which is a kind of a slight generalization of total variation distance. And so what we did is like we have kind of applied our logic to reason about differential privacy. So these are explanations about how differential privacy works and so on. But okay, let me just jump to this. This is actually the example which is interesting because we could actually come up with proof of privacy for algorithm where we actually asked the field experts, and they really don't know whether this algorithm would be private. So this is a very simple algorithm, which essentially is just one way to understand it is really like, I mean, I show it here in the case where you have an adversary, but there is even a simpler setting where you don't have any adversary. But let's say you have a list, and you want to return all the first k element within this list that are between two values a and b, and you want to do it in a private way for some notion of private. So it's a very simple algorithm, but it's actually something which is extremely hard to prove. So again, maybe this is useful to stress that the kind of formal verification that we are doing here is not really about scaling to a 1 million lines program, but we're spending our life reasoning about this 5 lines program, and they are very, very hard. So there have been kind of many published proof of actually much simpler variant of this. These published proofs are wrong. There has been recently a survey saying, look, all these guys did it wrong, but I fixed it. But of course, the proof in the survey was also wrong. And it's actually for something which is much, much simpler. And so we have a proof of this algorithm using coupling. And again, here I feel like we have this straitjacket of coupling. And the straitjacket of coupling is actually quite great because we have very easily a sense whether the proof will go through or not. And when we talk to, so some of this work is actually done with Justin Shu, who's a PhD student at UPenn, and he has 2 advisors. One is Benjamin Pierce, who's a programming language guy, but the other person is Aaron Roth, who's kind of a very big guy in differential privacy. So we have good people to talk to in the differential privacy setting. And I mean, it's not immediately clear to these guys in differential privacy that this stuff goes through. Okay, so we have kind of further generalization, which I will not mention, but the nice thing about having realized that this is coupling is like all the stuff that we have developed actually can be applied to a lot of settings where people have been trying to reason about the kind of convergence of probabilistic program. So which in my case means there might be a life after cryptography and privacy, but now we are gradually finding out that many of the techniques that we have developing, they can be applied to prove stability of machine learning algorithm, convergence of molecular evolution algorithm, and so on. So it's, I mean, it's a lot of fun. And so to conclude, what we've been doing is we've been developing program logics for provable security and differential privacy. They are kind of not only theoretical, but we have used them for a lot of examples, and we kind of able to go and deal with the state of the art based on this program logic. So it's kind of very good. Of course, all our proofs are interactive, but we can still do them in a reasonable amount of time. It's based on this beautiful notion of probabilistic coupling from probability theory, and there are kind of 2 main directions for further work. One is understanding coupling better, because coupling is well understood in the when it doesn't mix with the notion of distance, but for differential privacy or for stability of machine learning algorithm and so on, we have generalization of coupling. And again, so we don't know whether we're falling back into this half-baked mathematics that I was so worried about before. So it would be good to understand this better. And as I said, there are kind of many applications. So thanks for your time.
Yeah.
So for this kind of line of research, there's been various works in like approximate computing,
Yes.
where they actually try the logic of relational logic.
Yes.
What's your Mike Carvin did a lot of this kind of.
Yes, so they did a lot. I think it's in a rather specialized setting. But so what we've been doing, for example, so yeah, so I mean this crazy while rule that that I missed. One of the application of this crazy rule is actually looking at this loop perforation, and so we actually able to do kind of translation validation of loop perforation using this kind of rule. So this is a potential application. There are some people who are in a non-probabilistic setting. There are some people who have been using this notion of product program for translation validation. People at Bell Labs, I never remember their name, but I think they have a tool called Loopy at SAS this year. And so this is also, so they have a kind of language to do translation validation of loop optimization, and you can.
I guess it's just that in approximate computing, if I remember, mostly they look in discrete distribution.
Yes.
It's just discrete, right?
Yes.
So I don't know how the two logics differ. I mean, the PLDI is both, but 13 on the paper, Carbon and this one. It was also tracking multiple things at the same time.
Yeah, I mean, they certainly have a relational logic to try to do things. I think it's a bit different from the work which we had at the time, because a lot of the optimizations that they are doing, they're actually not structure preserving. And for example, they take a program which does a certain number of loop iteration, and yeah, I mean, the optimized program does, let's say, half of the loop optimization. And this is something which we could not deal with in the first place. We can now deal with it. I mean, I think we have an e-print called Coupling Proofs, our product program, which is on arXiv, which actually show application of this logic to loop perforation. Yeah, this is something I wish I knew more about, this kind of approximate computing.
Your coupling reminds me very much I mean, I have two questions. One is, your coupling reminds me very much about things like the quantum computing, like entanglement. So you have a correlation between two things, and the question is, as you smile, I guess the answer is no. Could you look also into quantum protocols using this?
No, I smile because I'm ignorant about. I smile of my ignorance. That's all. So
you didn't look in this?
No, I mean, this would be a very interesting direction to look into, but I mean, for us, cryptography has been some kind of a black hole, you know. We fall into this, we got stuck. And we thought like, oh, quantum computing would be nice, but we never made the effort.
So as far as I can see, what you're doing is you're going from Cartesian product to the tensor product,
Okay.
And therefore you have correlations or whatever you want to call it, the couplings. I don't say exactly how you go to the logic, but in the concrete case, you still have always the problem of dimension explosion. That's actually why people usually don't like it, because you get all combinations. Everything. So
yeah, but the way we set up our couplings, actually, we don't relate everything with everything. I mean, it's kind of a way of forcing invariance to be true. I don't think we have. I don't think we have dimensional problem.
I have a related question. So you have a bunch of assertion implication checks here. How do you actually check them?
This one.
Yeah. Are they
being
reduced to some kind of sort of theory?
Yeah, so these are kind of, I mean, they are formulating some kind of, it depends what your assertion language is, but it's a first order logic in some theory or higher.
You also had a sampling function in the next slide, I guess, which requires a much richer.
So you mean here on the existence of a bijection.
Yeah.
So it also depends how you want to set things up. There are actually two ways. If you actually, assertion language supports existential quantification of a function, you can actually try to push this here. If the question you are asking is like, how do you verify that f is a bijection, the way we actually do this is we require that you give f and g, and then you just have to verify the two inverse properties. So you have to give f and its inverse.
So I'm sure there are many more questions, but my job is also to defend the coffee break. So let's take a 20-minute break, but before that, let's think Gilles again.